Hello again. In this video, I'm going to show you how to calculate the KEQ for a reaction where water is oxidized into oxygen. And this happens in plants, although plants use light energy in order to do this. And we're going to show today how challenging this would be to do without light energy. And then in the next video I post, I will show you how light energy comes into play and how it makes this process spontaneous. So the question is to calculate the KEQ for this reaction. And in order to calculate the KEQ, I've got to know the delta G. And I'm going to calculate the delta G using the negative NF delta E equation. And from a table, I've gotten these values, these reduction potentials for the NADP to NADPH, and then from oxygen to water. And so this is our redox pair. And the way this works is first we have to calculate the delta E. And in order to do that, we need to figure out what's getting reduced and what's getting oxidized. But I just told you that water is getting oxidized, and NADP therefore must be getting reduced. So I'm going to take the value from NADP and put it in the front and put the value for oxygen to water behind it and subtract. So I'm going to get negative 0.324 minus 0.817. And this is going to equal the delta E of the reaction. And so this is actually going to be a negative value, which means it's not going to be spontaneous. So negative 1.141 volts. Anytime it's a negative voltage and we plug this into the delta G equation, we know that it's going to be endergonic because there's a negative here. So a negative value here means this is going to be positive and therefore endergonic. In order to calculate the delta G though, let's go ahead and plug everything in. Our N in this case is the number of electrons. And since the number of electrons in this reaction is more than it is here, because our coefficients are 2, we need to double them. So we have 2 NADPH that are required in order to oxidize 2 waters into 1 oxygen. Therefore, the number of electrons total that's transferred is 4. I'm going to put 4 here. Faraday's constant is 96.48 kilojoules per volt. And then, of course, our negative 1.41 volts. And then we put all this together, and we will get 440.3 kilojoules. And so that's how many kilojoules it's going to take in order for this process to go. And that's positive, so that means it's endergonic. And it is not spontaneous. Now just to illustrate this, let's look at the KEQ. So let's take our 440 kilojoules and put our R value in here, 8.314 times 10 to the negative third. Our T is going to be 298 Kelvin because we're at standard state, and then we're solving for ln of KEQ. So we're going to divide our numbers on the right by what's on the left. So that's 440 divided by negative 8.314, and then divide by 298. That gives me negative 177. I'm not going to write that down though, and then I take the e to the negative 177, and I get 7.45. So KEQ comes out to be 7.45 times 10 to the negative 78. That's a tiny number, which means that in reality, this is not going to take place. This is just too high of an energy barrier. So when you look at where the equilibrium lies, it's going to be strongly favoring the reactants to the negative 78th degree. So it is pretty much nothing is going to turn into a product. So this reaction effectively is not even going to happen at all, which is why we need light. And so in the next video, I'm going to show you how to include light into this equation and see how much energy light gives in order to make this process proceed. Because this does indeed happen in plants, but it will not happen without the help of light energy.